All right, last time we talked about central limit theorem, and I introduced you to what it was. You may not remember what it was. You may not quite get what it is. So we'll go back to this example again. When we talk about a central limit theorem, we're talking about this thing we call the sampling distribution. And in a sample distribution, what you're looking at is you're looking at all possible statistics, all possible sample statistics from any given sample that you look at. In our case, we're really focused on the sample mean, which we call X bar. So we're going to look at the X bars. And then we went through this example where we calculated the mean of the population. You have these 4 employees with their years of experience. We calculated the mean of these 4 employees. We got 4. Calculated standard deviation. We got 2.236, right? So what we did next is we took sample sizes of 2. We took different samples of size 2 with replacement. So we took different samples of size 2 with replacement like this, and we calculate the sample mean for every one of those. When we did this, remember when we did this, we have every possible sample mean on this graph right here. We have every possible sample mean, right? Every possible sample mean that you can grab of size 2 is sitting on this table right now. There are no other possible sample means. This is called the sampling distribution. You've looked at the sample mean or X bar when you looked at size 2 between 4 things. So when you do that, there are only 16 different means you can get. There are no other means you can get when you look at these samples. When we calculated that, we calculate the mean of the sample, what this is saying, the population mean, so that means you're adding up all of these values, you get 64, and you're going to divide by how many samples you have. Well, we have 16 different samples. This is called the population mean of the sample mean. So the population mean, so all of the sample means, what you're really saying here. When you find that mean, it's equal to 4. Standard deviation of all these X bars is 1.5811. We graphed this shape right here. We graphed it. Here go all the different sample means on the graph, all 16 sample means. You can see the center of the distribution is at 4. The standard deviation is still 1.5811. The shape, though, is the most important thing. This shape is now normal. That's what we're going to get to now. The shape is now normal. So this is what we call our central limit theorem. All right. And the central limit theorem focuses on sample sizes. So what's going to happen now is we're going to look at different sample sizes and different things like this. Normally, when we look at things, we find probabilities, for instance, we always looked at one thing. Now you're going to see sample sizes. When you see a sample size, you are looking for the magic number, which is 30. Anything bigger than 30 is what you're looking for. You are looking for any number bigger than 30. Because if it is bigger than 30, and we look at the sample mean, that tells us that the distribution of that sample mean will be approximately normal. And we want to do that because we want to use the normal function to calculate probabilities, all right? And the central limit theorem itself says that, states that the sampling distribution of the sample means will be approximately, and here's the key thing, it's approximately normal. It won't be fully normal, but it will be very close to a normal shape. And that only occurs when the sample is bigger, greater than or equal to 30. And it's greater than or equal to 30. And it has the following properties. So the mean of the sample means, that's what this is saying. The mean of the sample means is also equal to the mean of the population. We calculate the mean of the population for the 4 employees, that was 4. We calculate the mean of the sample means, that was also 4. So the first thing says that the mean of the sample means is equal to the mean of the population. And the standard deviation, which is what we call sigma x, the standard deviation of the sample means, the standard deviation of the sample means is the population standard deviation, which is sigma x, divided by the square root of our sample size. Divided by the square root of our sample size. And this is now going to be referred to as what we call the standard error. So this entire term is called the standard error. But the standard error is a standard deviation. It is a standard deviation. We just can't call it a standard deviation because we already have a term for a standard deviation sitting here. This is the standard deviation. Standard error is the standard deviation divided by the square root of the sample size. We're going to focus on this more in a second. And then here's what happens now. Both of these, this has to be met. It has to be greater than or equal to 30 first. But if we come back to our example real quick, Rn was this number right here. Here goes Rn. Rn is only 2. Rn was equal to 2. We were taking samples of size 2. When we took samples of size 2, though, we still got that normal shape. And that's because these numbers right here, when you look at these numbers in their population alone, they are already normal. So what I'm telling you now is this, and here's the other thing. We want to use the central limit theorem because we want approximately normal data based on the normal curve. We can have that if n is greater than or equal to 30. But if n is not greater than or equal to 30, then the other thing that can take place is the distribution can already be normal. If the population distribution is normal, then it doesn't matter what sample you take, it will also be normal. So if our n is less than 30, here's what you're looking for now. If your n is less than 30, in the problem, somewhere in the problem, it's going to state, so when n is less than 30, they will state that the distribution is normal. They will state that the distribution is already normal. So that's the big thing here. If n is less than 30, they will state that it's already normal. If n is greater than or equal to 30, you're going to assume that it's approximately normal based on the central limit theorem. And so I gave you this example, and we went through it, and we looked at the sample size, which was 100. 100 is bigger than 30. Because 100 is bigger than 30, by CLT, the central limit theorem, the central limit theorem says that the x bar, the sample mean, follows a normal distribution with a mean equal to the population. In this case, our mean of the population was 47. That's why we have 47 right here. And a standard error equal to sigma x divided by the square root of n. In this case, our standard deviation was 9. We took 9 divided by the square root of 100, which was our n, and got this. The thing I want you to notice is that the standard deviation for this is one person or one cell phone bill. The standard deviation for one bill is $9. When you look at a group of 100 bills, though, that standard deviation decreased to 90%. And that's because when you look at one person, it's hard to judge an entire population off of one person. That person may be the extreme person in the population. It's a lot easier, though, to judge a population off of 100 people. And that's because the more people you have in the sample, the more it starts to look like the population. And what I'm really saying is that as your sample size increases, so as n increases, variation amongst a sample decreases. So the standard deviation, the standard error, which is sigma x standard deviation, which is sigma x divided by the square root of n, should always be less than, the standard deviation, the population standard deviation, which is just sigma x. This value should always be less than, because you're looking at a sample versus you're looking at only one thing over here. All right. So look at this example here. It says that here's an example of sufficiently large condition not met. So sufficiently large means that n is greater than or equal to 30. Here's what we're going to do. It says assume the training heart rates of all 20-year-old athletes are normally distributed. This is important. Anytime they tell you something is normally distributed, the first thing you should automatically think to do is to draw a curve, a normal curve. But they tell me that it's normally distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn from the population and the mean is determined for each. Find the mean and standard deviation of the sampling distribution of the sample means. So my first question is this: do I have a sample size? Yes or no? Do I have a sample size? Somebody. I've been doing a lot of talking. Do I have a sample size? Thank you. The sample size is 4 here. So n is equal to 4. Now, here's what I want to do. When I get an n, I want my n to be bigger than 30. Is this n bigger than 30? Yes or no?
No. No.
No. So because it's not bigger than 30, right now I cannot use the central limit theorem. But there's one other condition that lets me use the central limit theorem. And that's if they state that it's already normally distributed. Have they stated that it's already normally distributed?
Yes.
Yes. So we can write it like this. Because the population is normal, X bar will follow a normal distribution. Because the population is normal, we need to really say by CLT, X bar follows a normal distribution or an approximately normal distribution with a mean equal to the mean of the population. What is the mean of the population?
135.
135. And a standard deviation equal to the standard deviation of the population, which is 18 divided by the square root of the sample size, which was 4. And so in this case right here, you do 18 divided by square root of 4 is just 2. So it's 18 divided by 2, which is just 9. Notice that the standard deviation was 18, the population was 18, but the standard error, let's knock out the standard error, is now 9. It decreases. And all we're doing right now, what we're really doing, this process is called, when you do this, is called describing. This is describing the distribution. That's what you're doing right now. Some of y'all may be like, well, is that it? This is it. If I tell you to describe this distribution, what I want you to do, I want you to tell me that it's normal, and I want you to give me its mean and the standard deviation. I want you to tell me actually that it's approximately normal with the mean and the standard deviation. All right. So that's the first thing. Now, here's why that's important. We're going to take the fact that it's normal to answer questions like this. This says a book publisher claims that its mean book length is 250 pages with a standard deviation of 70 pages. What is the probability that for a sample of 45 randomly selected books, the mean length of a book is less than 230 pages? The first thing I want to do is this. I want to identify a sample size. Do I have a sample size here?
45.
Thank you. So my N is equal to 45. What is significant about 45?
It's greater than 30.
So N here is greater than or equal to 30. By CLT, we're talking about the mean book length already, right? I want to find the mean length of a book. So that means I'm talking about X bar, the sample mean. By CLT, X bar follows an approximately, that means approximately, normal distribution. What is the mean of the population? What's the mean book length of the population? 250 pages, right? What's the standard deviation of the population?
70.
70. Now, for this particular problem, I have to divide that 70 by the square root of the sample size, which is 45. This is now called the standard error, but the standard error is just a standard deviation. If I do 70 divided by the square root of 45, I get this number right here. So for one book, the standard deviation was 70. For a group of 45 books, though, the standard deviation decreases to 10.4, we'll say 35. 10.435. Now, here's what they're asking, though. They want to know, what is the probability that for a sample of 45 books, the mean length is less than 230 pages? So I want the mean length. So I want the probability of X bar, the sample mean, to be less than 230. Because we're using central limit theorem, if we define this right here, what shape is the distribution going to be?
Bell.
Bell. So it'll be bell shape. So we'll draw a normal curve. We're going to draw a normal curve, right? And I know on a normal curve, where does the mean sit at on my normal curve?
In the middle.
In the middle. At what number here?
Oh.
250, right? So I know my mean sits at 250. And I'm asking you about what value here. What value do I care about?
Under
230.
230. So where does 230 sit at with respect to 250? Left or right? What side?
left.
On the
To the
left
left.
side. So we'll put 230 out here. And I want to be less than 230. I want to be less than 230. So which way am I going, left or right on my shade? When I shade this way,
Left.
which way do I shade? Left. So I shade to the left. Do we remember how to calculate normal probabilities? How do we calculate this normal probability? We can do a z-score. Let's do a z-score, all right? So what is z equal to? Z is equal to the x, 230, minus the mean, which is 250, divided by the standard deviation, which is, in this case, it's now 10.435. It's that standard error you just calculated. That's your new standard deviation, 10.435. We calculate that, we get 230 minus 250 divided by 10.435. I get about a negative 1.916, I would say negative 1.92. Hey, first off, why is the z-score negative?
Because
my
it's
z-score
on
negative?
the opposite side.
And it's less than the what though? It's less than what value?
The
It's less than the mean.
The
It's
mean.
less than the mean. And we know that values on the left-hand side of the mean should be what? Negative. This side should be negative. These should be positive. Do we remember how to calculate this negative 1.92? What do we do to calculate this? We go to our chart. We go to our chart here. Remember our chart? What side does the chart read, left or right?
Left.
What side is left? It only reads the left. Good thing we're calculating on the left right now. We are on the left. Everybody got that? So z is, I'm going to find z equal to negative 1.92. So negative 1.9 is here. 0.2 is going to be that 0, that's 1 is right here. It's about 0.0274. It's about 0.0274. So the probability of finding a mean book length of something that's less than 230 is about 0.0274. Which means this, here's what this really means. Pearson, a popular publisher of books, right, claims that on average, most of his books are about 250 pages long. You got that? We don't believe that claim, right? Or we just want to test that claim and see if that claim is actually true. That's what we want to do, right? So instead of just taking one book, I look at how many books here? I'm looking at 45 books. I'm going to take the average of those 45 books, the average page count of those 45 books. When I took the average, though, the average was what? 230. If they're saying that the true value is 250, but I've taken 45 books and got a value of 230, how likely is it to be true that 250 is the real claim? Well, this says it only occurs how often? The probability of getting a value of 230 or something less only occurs 2% of the time. So what is this really telling me then? This is telling me that this 250 is probably too high. Because I'm getting a value that's so low like this, it doesn't just happen by chance. There's something systematically that is happening. In this case, Pearson is probably overestimating the pages because they want to make more money by selling a bigger book or producing more pages. All right. That's what this is saying. So look at the next one. This says, or actually, let's look at this same problem, but let's do it in Excel real quick. In Excel, do you remember how to do this in Excel? Excel only calculates what side as well? Left or right?
Left.
It only calculates the left. Only calculates the left. So in Excel, we have a function. It's called equals, we do norm.dis. Norm.dis. We give it the x value first, our x value here. Our x value is 230. Where is it? Why can't I see it? There it goes. Our mean here was 250. Our standard deviation was 10 point, was it 435?
Yes.
Thank you. 435. And remember what we set our cumulative to? What do we set the cumulative to? What do we set that to? True or false?
False.
True.
Oh, true.
It's always true. Always true. Calculate that. Here's what I get, 0.027643. We got 0.0274 from the chart. Excel gives me a more accurate answer. Depending on what you're using, if Blackboard tells you to use the chart, you can use the chart. If it marks it wrong because you're not giving an exact answer like it wants, go use Excel, all right? Excel will give you the exact answer. So remember how to do that in Excel as well. So let's go to the next problem. Let's look at the next example. The next example says that the mean room and board expenses per year at four-year colleges is $9,126. You randomly select 9 four-year colleges. What is the probability that the mean room and board is more than $10,000? Assume that the room and board expenses are normally distributed, standard deviation of 1,500. First question I have is, do I have a sample size? Yes or no? Am I looking at a sample? Yes or no?
Yes.
How big is the sample?
It's the 9 colleges.
It's 9 colleges I'm selecting. Here's your select 9 four-year colleges. So my n is equal to 9. What's wrong with the number 9?
It's too small.
What's wrong with that number? Too small because it's not bigger than what number?
30.
It's not bigger than our 30 that we need to be, right? So because it's not bigger than 30, we can't use CLT just yet. We need more information. And then more information is going to come in the form of, they have to state that the distribution is already normal. Do they state that here in this problem? Yes or no?
Yes.
Yes.
Yes, they stated right here that it's normally distributed. So because the population is normal by CLT, X bar will also be approximately normal with a mean of the population. What's the mean of the population? What's the mean of the population?
9,126.
Thank you so much. Somebody else jumping in today. I appreciate that. 9,126. 9,126 is the mean. Standard deviation is going to be the standard deviation of the population, which is 1,500. I have to divide that by what though? What do I divide that by?
The square root of 9, which is 3.
Good. Square root of 9 here. Square root of 9. 1,500. Square root of 9 is just 3. So 1,500 divided by 3 is 500. So this is just 500. So notice what happened again. Our population for one college, one college's room and board expense is $1,500 when we look at that standard deviation. When we look at a group of 9 though, you have more colleges. That means it looks more like the population itself. The variation is going to decrease and it decreased down to 500. So now I want to know, what is the probability of that you get a mean room and board that is more than $10,000. So I want you to find the probability that X is greater than $10,000. Because we're using the central limit theorem tells me the shape is going to be what already? What is the shape going to be? Bell shape or normal, right? It would be normal or approximately normal. Draw a normal curve. What's at the middle of this curve?
9,126.
9,126 is at the middle. What side does 10,000 sit on? The left or the right?
Right.
All right, so we go 10,000 here. And which way are we going to shade? To the right or to the left? We want to be more than that. So which way do I shade, right or left? To the right. Good. Go to the right here. So again, we can calculate a z-score. Z is equal to 10,000 minus 9,126 divided by standard deviation, which is standard error, which is just 500 now. That's equal to 1.748. So we'll say about 1.75. This is equal to 1.75. Now, if I go to my chart, go back to my chart, right? So when I go to my chart again, go to my chart, I'm going to go up here to 1.75 and find the value of my chart, right? So 1.7 is here. 1.75 is here. That's equal to 0.9599. Remember why we draw pictures though. When I draw a picture here for this particular problem, what was that value again if I go all the way back over there? 0.9599. Okay. If I look at this picture, is the area here going to be 95 or 96%? Do you think it's going to be 96% over here? Yes or no?
No.
No, right? And that's because the chart only calculates which way?
To the right.
The left.
To the left. I'm trying to calculate which way though?
To the right.
To the right. So what do I need to do here?
Subtract.
I can do one of two things. I can do 1 minus that 0.9599, or I can go back and look at the chart and look at what? Instead of looking at 1.75, what can I look at?
Negative.
Negative 1.75. If I calculate the right, I can always flip the sign to find things, all right? So if I go look at negative 1.75, negative 1.7 is here. Negative 1.7 is here. And that value right here is here, 0.401. That's 5, I think. Let me make sure. Yeah, 0.0401 is the answer. If I do 1 minus 0.9599, I also get 0.04012. So that value here, the probability of being bigger than this is 0.0401. I can also use Excel for this if I wanted to. Excel, when I do Excel this time, when I get that answer, I just have to go back and subtract it from 1. All right. So I go back and subtract it from 1. So what I want you to realize is that central limit theorem is just an extension of the normal probabilities that you've been calculating. And the real big difference is you're dividing by a sample size this time. You're dividing by a sample size. In all honesty, you've always been dividing by a sample size, but your sample size has always been 1. And because you're dividing by the square root of 1, which is just 1, it leaves the standard deviation at its current value. Now you're dividing by actual sample size, which should decrease the standard deviation every time. And are there any questions on that? Y'all okay with that? That is the central limit theorem. I'm assuming y'all okay. Y'all ain't say nothing.
Okay.
All right, cool. Thank you for talking. I appreciate it. So next thing I'm going to introduce you to is this then. Now that we have the central limit theorem, and the central limit theorem is vital for the rest of statistics, because what it does now is it tells me that even if I don't know the shape of the distribution, and generally speaking, we don't know the shape. And by shape, I mean it can be right, left, or symmetric. We don't know those shape. But it doesn't matter the shape if the sample size is big enough. If the sample size is already big enough, the shape doesn't matter. And I can do a whole lot of things with a normal curve now. And the next thing I'm going to talk about is what's called a confidence interval. A confidence interval, right? And so let me introduce it to you like this. Any of y'all watch The Price is Right? Ever saw The Price is Right? You know what that is?
Yes.
Okay,
Yeah.
cool. Good. I'm glad somebody said that because I feel old when I ask people that and they don't know. Price is Right, if you don't know what it is, it's a consumer price game where they try to guess prices basically on the show, right? So in this particular game, it's called the range game I'm about to show you. And in the range game, there's a contestant, her name is Linda, right? And she is going to try to guess the price of a trip. She's going to try to guess the price of a trip, all right? So I'm gonna play this video. Y'all watch it and we'll talk about it in a second, all right? Hey, can y'all have sound?
No.
Y'all hear it?
No, we can't hear it.
Let me see how I
No
get the sound to play.
sound.
Hold on.
And it's going.
That's me. I have sound in my ears, but y'all don't have sound in y'all ears. I gotta figure out how to get y'all sound. 1 second. What do I go to? That's like a settings type of thing, huh? That's on the wrong thing though. Well, I want to show y'all this video, but I don't know how to make it play where y'all actually have. Oh wait, I know how to do it. Share sound. There it goes.
How's it going? Good.
Hey, how about now? Y'all can hear it?
Yes.
Okay, cool. Thank you.
Made it to the Price is Right stage.
Oh my God, yes.
Where are you from?
Pittsburgh.
And what do you do in Pittsburgh? I won't hold it against you. It's not football season. During baseball season, I love everybody in Pittsburgh.
I'm an artist.
Yeah, you're an artist? Oh, how about
Yes.
that?
Yeah.
Hey, George, I think artists need this next prize, don't you think?
Linda, they happen to have some great artists on your trip to Rome! You and a guest will fly round-trip coach from Los Angeles to Rome for a 6-night stay in a lovely room with a Vatican view at the Hotel Atlante Star, conveniently located within walking distance of St. Peter's. Daily breakfast included. Plus, you'll sample gelato, pastries, and more during your 4-hour food walking tour.
Look at that,
All right. So
great.
let's talk about that real quick. So she's gonna win a trip. She can win a trip to Rome, right? And in this particular game, they told her that she gets they said like 5 nights, 4 nights, I think it was something like that. All expenses paid, airfare, food, all that stuff, right? All she has to do is, let me let Drew explain.
man. Trip to Rome for an artist is like a dream, right? Yeah,
Yes,
that's
yes,
where it is. It's the
for
most
sure.
beautiful city. Now, here's the price. Hidden in this little scale right here, all right? I don't know where it is up there. That's for you to decide, but it's round-trip coach for 2 people from Los Angeles to Rome. 6 nights, all right? 6 nights, 2 people. See this little red area right here?
Yeah.
That represents $150 range. It's going to climb up the scale. When you see the price of the trip to Rome in the red area, you're going to hit the button. If you're right, you're on your way to Rome.
Okay.
If not, you get to spin the wheel. Linda, you ready?
Yes, I'm
Here
ready.
we go. Start it up.
Margie! 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 Margie!
Let's get to Rome. Let's get that trip. Round trip coach for 2 people from Los Angeles to Rome. 6-night stay, Vatican view room.
Hey, y'all understand what Linda had to do, right? Everybody understand what she had to do?
Mm-hmm.
She had to try to guess their price of that
Yes.
trip
She had to guess
Yeah.
the price.
Good. By putting inside the red
variation of
area. Does everybody understand that?
150.
So right now she's guessing that price of the trip is what? About 9,200 and we'll say $75, $80. I see that, right? That is her actual estimate. Her estimate of the trip is 9,000. We'll say 280, 9,280, right? But they're giving her a $150 range, and that range is split exactly in half. So how much is on the top of 9,280? You want to tell me that?
$75.
Right. And how much is on the bottom of it?
75 more dollars. or
$75.
less-
Well,
75 less
how'd you
dollars?
get that? How'd you get that $75? Can you tell me that?
Yeah, divide the range in half.
Divide the range in half. Thank you. We're splitting that 150 in half, right? So let's talk about this real quick before we keep going. Why are they giving her a range? Why are they giving her a range? Why not just make her try to guess the exact price of the trip?
To give her a higher chance of getting it?
To give her a higher chance to get it and to actually make the game more competitive, more watchable, right? Do you think it's possible for her to guess the exact price of this trip? Yes or no?
It's very unlikely.
It's very unlikely. It is possible, but it's very unlikely, right? So what are they telling her she has to do now? Does she have to get the exact price?
No.
No.
No, she
No.
just has to do what? She has to put the price where at?
In between,
Where does the price?
somewhere in
the
there,
in the
On the
red area.
main?
Does
in
everybody
the
understand that?
range.
So she has to put the price in the red area. We all understand that, right? That's the game right here. So the question is, do you think Linda put the price of the trip in the red area? Well, let's see.
Boom. Just
I hit too
below.
hard.
No, you didn't hit too hard. You can kick it. You can punch it. You can't break this game. This game's been around for like 27 years, something like that. Been around for a while. You're not gonna hurt this game. You're from 9,200 just about all the way up to 9,350. So a little over that. Let's see if you're going to Rome. Ready?
How do I know if I win?
1, 2, 3. You got it!
So, did she win? Yes.
Yep.
Was her estimate correct? Was her point, we'll call it a single estimate, at 9,280? Was that the right answer? No. But did it need to be the right answer?
No.
No,
No.
right? It did not need to be the right answer. She just needed to put it within that range. So we're going to move to this thing now that's called a confidence interval. We're going to move to this thing called a confidence interval, right? And here's what we've been doing for everything so far. Everything we've done so far, we've tried to give a single estimate of what we think the value is. When you give me the mean, you're giving me a single value for the mean, right? And we can do that because we actually have information about the mean. We actually have that information about the mean. But when Linda started playing this game, did she know what the price of the trip was? Yes or no?
No.
No, she had no clue what the trip was. So when we do confidence intervals, we start off with this assumption that we have no clue. We don't know anything. We don't know anything, all right? And we're gonna go gather data now, all right? So the way it works is like this. We're gonna talk about this thing that we call confidence. And when I talk about this, I'm gonna build it from the actual video that we just watched. And a big part of this is that we're going to focus on the central limit theorem. We're going to focus on the central limit theorem, which, what do we look for in the central limit theorem? N greater than or equal to 30, right? So a confidence interval itself, I got a whole lot of stuff that I don't want to talk about. I guess I'm going to talk about it now. Let's start with a confidence interval. Let me define what a confidence interval is. A confidence interval is a range of plausible values. It's a range of plausible values. A range of plausible values is what we're going to call this. It's a range of plausible values. Everything we focused on so far has been what we call a point estimate. All right, it's been called a point estimate. And a point estimate is a single value. It's a single value. And when we say single value, really mean a single guess, or it's a statistic. This is a statistic. And so if we think about the range game real quick, here's how it works out. You had a range of how big again? How big was your range?
150.
150. So this range itself is $150, right? Now, Linda tried to guess right here, and this right here was $9,280. We'll say 975, but that'll make it a nice number. $9,275. That'll make this nice when we calculate these other values. So this right here is the point estimate. That is the point estimate. That is the single value that she's using to guess the entire trip. Yeah, I understand that. That's the point estimate. The interval, though, now is formed around the point estimate. The interval now is formed around the point estimate. And these are all going to be other plausible values within a range for the trip. The goal is not to guess the exact price of the trip. That would be nice. The goal, though, is to put the exact price, which that exact price was, I don't know what the exact price was, but
the exact price was
anybody remember?
9,304.
Say it again. 9,384.
hmm
I don't, something like that. It don't really matter. I don't think it does, at least. It's not gonna matter. I just want to show y'all. Let me group these. Oh, there it goes. That's the one. All right. So the exact price was somewhere up here. I think it was 9,324. Let's say it was 9,324. It doesn't really matter. That's the exact price. This price right here are the true values, what we call that. We call it the true value. This is also known as a parameter. This is also known as a parameter. Remember, the parameter is the true value from the population. It's the true value. The point estimate is known as a statistic. And this is a guess of the true value. The goal here is to put the parameter inside of that interval using the point estimate, to form the interval. And so now here's what happens. If we carry the point estimate out all the way across like this, above here is $75, below here is $75. So we can form an estimate by saying now 9,275 plus 75. So the top of this interval is 9,350, and then 9,275 minus 75, and the bottom of this interval is 9,200. So as long as the trip falls between 9,200 and 9,350, she wins. How did we get that? Well, look what we did. We added 75 above and 75 below, and we put a number in the middle. Now, here's how this really works in real life then. We're going to draw different samples. And we're going to form our sample or form our interval around whatever our sample mean is. If I draw a sample, do you think you will get the exact same mean in your sample? Yes or no? If I draw a sample, do you think you'll get the exact same mean as me in your sample? Yes or no?
No.
No, probably not. We're probably gonna get all different means. You understand that? We will probably all get different means. But here's what's gonna stay the same. We will all have this $150 range. We will all have this $150 range. So the only thing that's going to move the range is going to be where you stop your game at, I guess. How you can say it. That's gonna be the only thing that moves the range. But this part is fixed. That won't move at all right? And so we're going to talk about this thing that we call confidence first. All right. And the confidence level gives the interval which we expect to find the true mean value if we use this method a whole bunch of times or a certain percent of time. So if I played this game 100 times, and I was 95% confident, that means when I played this game 100 times, I'm going to stop this value at different spots. Those 95 spots that I stop it at, maybe those 100 spots that I stop it at, maybe 100 different numbers, by the way. Some may be the exact same, but you may have 100 different numbers. I understand that. If I am 95% confident, and we say 95 because that is generally the default confidence level. If I am 95% confident, that means I will capture the true value 95% of the time. Let me write that out right here. If you say you are 95% confident, let me define what that means. This means that if an experiment is repeated over and over again. So the first part means you're going to do it a whole lot of times. I'm saying 100 because 100 is a nice number to calculate percents out of. But if an experiment is repeated over and over again, we will capture the true value. The true value is also called the parameter. We'll capture the parameter 95% of the time. We'll capture the true value of the parameter 95% of the time. And generally speaking, when we talk about confidence, and if I am 95% confident, let's say I do it 100 times, how many of my different intervals are going to have, remember these intervals are all moving. They're the same width, but they're all moving. How many of my different intervals will have this value in it? If I capture it, if I do it 100 times, and I'm 95% confident, how many will have this value inside of it? Can y'all tell me that?
95% of them.
So that's going to be what? If it's 100, what's 95% of 100? What's 95% of 100? What's 95% of 100? What's 95% of 100?
0.9.
5.
Somebody said it, it's 95. It's just
95.
95. So if I have 100 different intervals, right? 100 different intervals, 95 of those intervals will capture the true value. How many are going to miss it?
5.
5 of them. That's what I want you to understand what we're doing here. And here's what you're doing. Here's another graphic of how we can look at it. Let's say that we know we have a true value right here at 5. That's the true value. This is the parameter. We're going to form intervals around that. And here's what our intervals are going to look like. We have intervals that do something like this. Some intervals that do something like this. Some intervals that do something like this. They're all the same length, though. They're all the same width. Everybody got that? They're all doing this. And then you have one interval that does something like this. These are your intervals. This interval, and this interval, what are they all doing?
They're staying within the parameter.
And they're capturing the true value. These all capture the true value. What is this interval? This interval does what? This interval out here, it misses. This one misses. And what that really means is that, remember, in all these intervals, you have a mean sitting at the middle. And the mean is what's actually moving things. You understand that? So when I pulled a sample mean, it was within the plausible values. When I pulled a sample mean, it was within plausible values. Sample mean, plausible value. When I pulled this sample mean, though, it tended to be bigger than the plausible values. And it missed. That means you have too many big values in here. And that can happen. So when we talk about confidence, what we're really saying is that if we do it over and over again, and I'm 95% confident, I'm going to capture it 95% of the time. I'm going to miss 5% of the time. So here's what happens to confidence then. If we increase our confidence, so here's how we look at confidence. Confidence is basically the width of the interval now too. So the width, when am I going to be more confident? If I say I'm 80% confident or 90% confident, which one is more confident, 80% or 90%?
90%.
90%.
90%. You're 90% confident means you're going to capture the true value how often? How often do you capture the true value? 90% of the time.
90%.
If I'm 80% confident, I'm only going to capture it 80% of the time, right? So question is this, which one has a larger width? Do you think you have a larger width with more confidence or a larger width with less confidence?
More confidence.
More confidence. The bigger the confidence level, the larger the width. The bigger the confidence level, the larger the width. So confidence is increased when the confidence level also increases. All right. So confidence is increased when the confidence level also increases. So our confidence level then, our confidence level is what we're saying at 95%. That's our confidence level. If we increase it, if we increase that, we get a wider width, we get a bigger width. So here's how we find that actual confidence level. That confidence level is based on the central limit theorem. It's based on the central limit theorem. We want n to be bigger than 30, or we want something to be approximately normal. And what's going to happen is we're going to find these things that we call critical values now. Critical values. A critical value is the, write it out. A critical value, also known as Z star, or you may see it called Z sub half alpha. Z sub half alpha is also what we call a critical value. I use Z star. Some books, some people use Z sub half alpha. And this is the Greek letter alpha right here. The fish is the Greek letter alpha. You're taking half of it, and it's written as a subscript. So that's why it's called Z sub half alpha. You're taking half of the alpha value. Now, this value itself, this critical value, is a right-hand z-score. It's a right-hand z-score that sits at the edge. It sits at the very edge of the confidence interval. It's a right-hand z-score that sits at the very edge of the confidence interval. So we draw a normal curve first off because it's a z-score. All z-scores sit on a normal curve, by the way. If I say that I am 95% confident, here's what I'm doing. I'm 95% confident. That means that within this range right here, I'm going to capture the true parameter 95% of the time. If I want to know how big that width is, I'm going to create this thing that we call a critical value. This value right here is your z star. Whatever you get for this z star, this value is going to be the negative or the opposite version of it. We always find this one right here, the positive, all right? So here's how we do this. If we want to find 95% confidence level, this means that we want to find where 95% of the area is under the curve, right? And so the way we do it, if I want to find a 95% confidence level, right? I put 95% underneath the curve. How much of the value, what percentage of the values are not underneath the curve then? If 95% underneath, how much is not underneath?
5% is outside.
5% is outside. But we have to split that 5% in two tails. Y'all got that? So how much is on the left?
1.5.
0.5.
Try to point, if I have 5%, how much
Sorry.
is on the left? How much is on the left have 5%? 2.5% on the left. How much is on the right?
0.5.
2.5. So over here is 2.5%, and over here is also 2.5%. I want to find the z-score that corresponds to this value right here, that right-hand z-score. That's the critical value I'm marking right there. In order to do that, I need to find the area to the left of this particular value. I need to find the area to the left of the particular value. How much area is to the left of this value?
97.5.
Good job. It's 97.5. This is 97.5 that you're looking at, by the way. So what I want to do then, I want to find the z-score that corresponds to 97.5% of the data. So what can I do? I just go to my chart. Go to my chart. I probably need a new chart here pretty soon. Let me erase this stuff on this chart so we can see it better. And you can I'm erasing negative. You only really need to look at the positives, by the way, because z-scores are always right hand positive values. The z-score is always a positive value. So if I want to find the area that corresponds to 97.5%, I need to go inside the chart. I go inside the chart, and I see that value is sitting right here. That value is sitting right there. So here's that value. Where'd it go? Oh, here's that value sitting right here. That's 97.5%, 0.975. So I read that. What is the z-score that corresponds to it? That value is 1.9. This value is 0.06. So the z-score that corresponds to 97.5% is 1.96. And look here at this curve, what number is sitting on that curve already? We have 1.96. That's how I get the value of z equals 1.96. So the process is like this. I'm going to give you a confidence level. I'm going to give you a confidence level. For instance, I'm going to give you 86% as a confidence level. The first thing you're going to do is you're going to draw a curve. I'm going to draw a curve, a normal curve. I'm going to ask you for this curve, how much data sits on the inside of the curve? How much data sits within the bounds like this? How much data sits inside of that? Can anybody tell me? 86%. If 86% is on the inside, how much is on the outside? How much is over here?
7%.
How much is over here? 7% to both sides, right? How are we getting 7%? 86% on the inside. How much on the outside? 14%, right? Cut 14 in half, you get 7% here and 7% here. I'm looking for this z-score right here, the right-hand z-score. So I need to find out how much area is up to that 7%. How much area is up to that 7%? I mean, up to this, I'm sorry, up to the z-score right here. How much area is up to the z-score? Well, I have 7% plus what?
93%.
Good. So 77% plus 86% is 93%. So what do? I need to go into my chart. And I need to find 93%. Oh, it's right here. Good. So 93% is about, when I look at this, 93% is about, like it's about 1.4, we'll say about 1.408. So 1.48, this value right here. So this critical value that corresponds to this value then is just 1.48. Now, I can be more accurate with this if I use Excel. And I'm going to show you how to do an Excel now. So using Excel, remember how we do this. We've done this before in Excel, by the way. In Excel, you're going to use the norm dot norm dot inv. Norm dot inv is the function you want to use here. You're using the inverse normal. You're going backwards. You're giving areas. You express the area as a percentage or as a decimal. So we said we had 93%, so we'll do 0.93. Our mean, because we're on a normal curve, we're going to just put, because we're on a standard normal, we're going to put 0. And you can do 1 for the standard deviation. The other function you could have used, which is one I think I told you how to use, was norm.invs or something like that. You can use either or because you're finding z-scores. It's just that when you use this function right here, just make sure you change your mean to 0, your standard deviation to 1. If you're on a normal curve. I mean, a standard normal. So when I do this, I get 1.475791. That's more accurate, but the actual value is 1.48, which is what we calculated a second ago. So it's easier to do inverse normal problems using Excel because Excel is already calculating everything to the left. And that's what you're essentially doing here. You're calculating values to the left. So if we look at the next one, if I want to be 90% confident, again, here's what I do. I draw a normal curve. How much area is on the inside of the normal curve?
90.
90% on the inside. So it puts how much on the outside?
5 on each side.
5 on each side. So it's 5% here and 5% here, right? And when I calculate these values, remember, I'm calculating up to that right-hand z-score. So I'm calculating up to this z-score right here. So I want to do inverse. I want to look at the chart. And I want to look for what value? I want to look for 0.95, right? I want to look for 0.95. And so when I go to my chart again, 0.95 on the chart is sitting right here. It actually sits in between these two values exactly, by the way. 1.6 right here. It literally sits in between these two values. I lied, to the right of that one. This one is 5% less. I mean, 0.0005% less. This one is 0.005% more. So it's literally in between those. If it's in between 4 and 5, then we can write this as just 1.645. So you can actually get this from the 3 decimals because you're actually in between those two values like that. So when we write this z-score is equal to 1.645. Or you can call it 1.65. Or if you go to Excel again, in Excel, equals norm.I, it did not like that. What are y'all seeing right now? My screen's stuck, right?
Yes.
Y'all can hear me? Okay, thank you. Hold on, my iPad cut me out. Let me get back in. All right, coming back to this. So if I want to find the value, again, I'm going to do norm.inv. We're doing 0.95 here. The mean is 0. Standard deviation is 1. And you get 1.64485, or if you want to 3 decimals, 1.645. You could have also used this function here. I think it's the one I told you the last time. If you're doing z-scores, you can always use the norm dot I. Oh man, I messed that up. Hold on. Equals norm, and you have the one that says norm dot SINV. This is going to calculate straight z-scores, but all you got to do is give it a probability. So if I give it 0.95 like this, it'll also give me that value. That's using the S function in front of the INV. That just means it's a standard normal. So let's look at the next one in the example. Got that cut off too. I hope it saves all that. All right, good. So 98%. If I want to calculate 98%, how much is on the inside again?
98.
98% on the inside. How much do we have on the outside then?
1 on each side.
1 on each side. Thank you so much. So we have here. This is the Z star I want to look for. This is 98%. We have 1% sitting over here and 1% sitting over here. So I want to calculate up to this value. What am I going to look at then?
99.
Look at what percent? 99%. So I'll go to Excel and I'll do equals. I wonder if you type in just norm.inv and type in 0.99, will it automatically register as a, now you gotta go to mean 0, 1. There you go. 2.2326. You want to go 3 decimals. If you go to your chart and find that 99%, so Excel tells us 2.326. Go to your chart real quick. 99%, and we'll show on this chart. Let me go to the other chart real quick. I didn't give y'all enough chart there. If I want to find 2.236 on this chart, 2.2 is sitting here. No, 99%. You'll find that in the table actually. So if I find 99% in the table, it looks like it's sitting right here at this value. And again, it's looked like it's, now that one's 1, so that one's closer. So we'll go from here. I missed that. 2.3 is that value. We had 2.326, which rounds to 2.33, which is what we're getting here, 2.33. So this value, this z-score, is equal to 2.33. Let's stop real quick and notice something. Which value, what's happening to the z-score as you're increasing confidence? So I went from 86
larger.
to, what's happening to it?
It's
I'm
increased.
sorry. It's increasing. Thank you so much. So what? I went from 86 to 90 to 98%. As I did that, what happens to your z-score? Your z-score is going further and further out. It's getting wider. All right. So this tells me that the more confident I am, the larger the z-score, the critical value has to be, the wider the interval will be, because the z-score is going to determine the width of the interval. It's going to determine width, all right? So what this does then, that z-score is going to help us find our margin of error. And we call the margin of error E. E. And the margin of error, you look at it like this. When you look at Linda's game, her margin of error was 75, right? And here's how it works. The margin of error places a value in the middle, a point estimator in the middle. Our point estimator will be X bar. We're gonna have X bar sitting in the middle. And then from there, we're going to give X bar error to the right, error to the left. This is minus E, this is plus E. So you have positive error, negative error. It gives you your bounds. And E itself, E is equal to Z star times sigma X divided by N divided by your sample size N. All right. E is equal to Z star times sigma X divided by N. I don't feel like that is the right formula. I am having a brain freeze. Hold on one second. Let me make sure I give y'all the right formula there. I'm sorry. Z star times sigma divided by N. Yeah, that's right. All right. So and here's what's going to happen to that value then. Notice that when we increase the level of confidence, that affects Z star. That affects Z star, right? And it also affects the critical value, how big the critical value is. So if we want a larger margin of error, here's what happens. We tend to get a bigger, we tend to use a larger confidence level, which makes sense. We said that if your confidence level is 86% versus 98%, the 98% was going to be bigger, going to be wider. That's because this formula is affecting that, all right? So here's how we actually find a confidence interval then. A confidence interval is found, I just showed it to you right here. It's X bar, your estimate, whatever you're estimating with, plus or minus some error. Well, our error, margin of error here, E is equal to this right here. So the formula for this, I know I wrote this wrong. Now I see what I did wrong. Hey, this is not the right formula. It's Z star times sigma over the square root of N. That makes more sense. Oh, that's not right. This looks a lot better. I was trying to figure that out for long. It's Z star times sigma over the square root of N. All right. That's what this is. And anybody tell me what this term is called right here? What is that term called? Have we seen that term before? Have you seen the standard deviation divided by the square root of N? What is that
Standard
called?
deviation.
Try it again. It's close. It's called the actual. The top part is called standard deviation. Dividing by the square root of N, we call this the standard error. It is a form. It is a form of the standard deviation, but we saw it in the central limit theorem formula, right? So it says to get your margin of error, what you're going to do is basically multiply your critical value, how far you want to spread the width out, times the natural error that already occurs in the sample. All right. And then if we know that, we can actually calculate a confidence interval by taking the, here it goes, X bar, our estimate, which is X bar in this case, X bar, and then adding and subtracting the margin of error, which is Z star times the standard error, which is sigma X divided by the square root of N. So this is how we calculate a standard error. This is how we calculate this value, all right? This is how we calculate actual confidence interval. Come on, later. Let's actually do a problem. This says, suppose that a sample of n equals 36 cereal boxes has a mean of 362 grams with a known standard deviation of 15 grams. And here's what we're going to talk about now. Certain problems you're going to do, you're going to know the standard deviation. It's going to tell you that assume the standard deviation is known, or that you know the population standard deviation is this. If you know the population standard deviation, or if you assume that the population standard deviation is known, if a standard deviation is known, a known standard deviation is called sigma. That means you know sigma. A known standard deviation is called sigma. We're going to start off assuming that we know the standard deviation. If you have a known standard deviation, then we always use, you're going to use a z critical value. You always use a z star. If we have a known standard deviation, we always use a z critical value. There's going to be some problems where we don't know the standard deviation, and we're estimating the standard deviation based on the sample. When that happens, we'll use a different critical value. But for now, we're going to know the standard deviation. So it says, suppose that a sample of n equals 36 cereal boxes has a mean of 362 grams with a known standard deviation. This is key right here, by the way. A known standard deviation of 15 grams. Find the 95 and 99% confidence interval. Which interval will be more accurate? Which interval will be more precise? So first part, question I have is, do we have a sample size? Yes or no?
Yes.
And how big is that sample size?
36.
36. What's significant about 36?
Greater than 30.
Greater than 30.
It's greater than 30. So because it's greater than 30, I know I can use the central limit theorem, which tells me that the distribution is approximately normal. But I want to find confidence intervals here. So in order to find a confidence interval, I need these things right here. Here's the formula for a confidence interval. It is x bar plus or minus some critical value, which we will call z star, times the standard deviation, which we call sigma, the known standard deviation here, divided by the square root of n. This is the formula for a confidence interval. So when I calculate this right here, do I know what the standard, do I know the value of the mean, the sample mean? Yes or no?
362.
362. And how do I know it's a sample mean, by the way? It says, suppose that a sample has a mean of 362. That tells me I'm dealing with a sample mean. So this is 362 plus or minus my z star. Well, if I want to do my first interval is at 95%. What is the z star for 95%? How would we find that? Do you remember how to find that? Draw a normal curve. How much area is on the inside of the normal curve?
95.
95. How much on the outside then?
5.
Over here is 2.5. So I would do norm dot I and V and do 0.975. We've already calculated that z-score, by the way. Does anybody remember what that z-score is?
97.5.
Try it again. That's the actual value, but what's the z-score for it?
Oh,
What's the actual z-score?
1.96.
1.96. One of the few things that you should remember is the 95% confidence interval critical value, because that's a general, that is the default that most people default to. They will normally talk about the 95% confidence value. And for a z value, that's 1.96. So you can memorize that 1.96. So here z star is 1.96. Right? Times your standard deviation. Well, the standard deviation from the problem is said to be what? It's known to be 15 grams. Known to be 15 grams. And we'll divide that by the square root of what? The sample
36.
size is 36. That's it. This right here, this back part back here, this is called the margin of error. That's your margin of error. That's the margin of error E. That is the margin of error E. Now, to actually calculate this, we need to calculate the value of E first. We're going to calculate the value of E. So I'm going to multiply 1.96 times 15 divided by the square root of 36. All right, and so when I do that, I get 4.9. So this value right here, E is equal to 4.9. If I want to find the actual interval itself, then the interval goes from 362. The lower bound is minus 4.9. Here's what that plus or minus means. The upper bound is 362 plus 4.9.
I have a quick question.
I'm listening.
How did you get that 1.96? I think that's the only part that confuses me.
That's the critical value for the 95% confidence level. So remember, we were doing this in the chart. We did it from the chart, and I can do it from Excel as well. I do it from Excel because it goes by quicker. But remember, you're going to do norm.inv, or you can do the one with the S in front of it. If you do the one with the S, it's a lot quicker. But it doesn't matter. You can do the SINV or you can do the INV. If you do INV like this, we said that that area for 95% was actually, you have 95% sitting in the middle. So that means you have 5% on the outside, but you have to cut that in half. So it's 2.5 on the left. So you're going to add 2.5 to 95, you get 0.975. When I do this with that, set my mean to 0, my standard deviation to 1. That gives me 1.95996, which is 1.96. That is the critical value Z star.
Okay.
It also
gotcha.
comes
Thank
from
you.
that also comes from looking at that table that we did too, by the way. You can look at the table. If you go back in your table one more time, where is it at? Go back in your table right here. 95% sits about right, 95 or 97.5% sits about, it's right there actually. It's right here, 9 there. So if you do this, you go 1.9. That's equal to 1.96. So you can find it like that too. So we get that 1.96 from that, and then we plug this in. Here's what we get. Here is the lower bound of the interval. Here's the upper bound of the interval. So we just need to calculate that. 3.62 minus, or 362. Minus 4.9 is this. $357.1 lower bound, 362 plus 4.9. Where'd it go? 366.9. So what we're saying now is this. When we talk about confidence, what you're really saying is now, you're pretty confident, you're confident that 95% of all intervals, if you do it this way constructed, will fall between these two values. All right, 95% of the time we're going to capture the true value using these two values right here. Right. So the actual interpretation of our thing is going to be read like this. We are 95% confident. We are, in this case, 95% confident that the true mean, so whatever our true mean is, in this case, we're talking about, what are we talking about? Cereal boxes, right? Talking about cereal boxes right here. So because we're talking about cereal boxes, I'm going to define this. The mean itself is the true mean weight of a cereal box. It's the true mean weight of cereal boxes. So I am 95, from our number, we are 95% confident that the true mean weight of cereal boxes is between our lower bound, which is 357.1, and our upper bound, which is 366.9. That is a general interpretation of how you say it. So again, I'll write it out here so you can see it. Back there real quick. We are 95% confident that the true mean weight of cereal boxes falls between 357.1 and 366.9. For 95% confident, the true mean weight of cereal boxes falls between 357.1 and 366.9. Furthermore, if we kept doing this a whole bunch of times, and we did this a whole bunch of times, 95% of all intervals, 95% of all the intervals will fall within these two values, within the interval constructed. Which means that if I do it a whole bunch of times, if I did it 100 times, for instance, 95% of my intervals should fall within these two values that we constructed. So let's try example 2. You want to estimate the mean number of hours people spend sleeping. In a random sample of 12 people, the mean number of hours spent sleeping was 7.2 hours. And from past studies, the standard deviation is known. Here's a key thing, by the way. Because they tell me it's known, when they say the word known, if I have a known standard deviation or a known standard deviation, known sigma, use a z critical value. So the standard deviation is known to be 0.75 hours and the population is normally distributed. Construct a 90% confidence interval of the population mean. First question is this: do I have a sample size? Yes or no? Sample size, yes or no?
Yes.
What is the sample size? Can somebody tell me that, please, real quick?
12.
12.
12. What's wrong with the number 12?
Small.
It's
It's not bigger. It's not bigger than 30, right? So what else should I look for then? They need to tell me what. If it's not bigger than 30, what else should I look for?
That it's normally distributed.
Is it normally distributed?
Yeah.
Look right here. And the population is what? Normally distributed. I need that to calculate the z value, to calculate my critical value. That's why I need that. So it's known to be, so I know my critical value now is going to be a z star because it's known. I want the 90% confidence, the 90% z star. How much is on the inside? 90%, right? How much on the outside? How much is on the left-hand side over here? 5%. So I'm going to do that for my z star. This is equal to norm.inv 0.9501. .9501. Anybody calculate that? Or do I remember what it was from the previous problems that we did?
1.65. Or 1.64.
645. We'll go 1.645 here. And 90% is another common value you might want to memorize too. 1.96 for 95 and 1.645 for 90% of general values that you might want to memorize. The other part then is we need to construct a 90% confidence interval from the mean. So we need the sample mean. What was our sample mean?
12.
Thank you. Our sample mean, that was the sample size. What's sample mean? The mean number of hours that spent sleeping is
7.2.
so x bar is 7.2. X bar is 7.2. Standard deviation is known to be 0.75 hours. So sigma equals 0.75. If I want to calculate the interval, remember the interval is just this. It's x bar plus or minus z star times sigma over the square root of n. this will just be 7.2 plus or minus Z star 1.645 times sigma 0.75 divided by the square root of 12. And so when I calculate this value, I'm going to do the margin of error first. So it's 1.645 times 0.75 divided by the square root of 12. So my E, when I calculate this right here, E is equal to we'll say 356. E equals 0.356. So I'm going to do 7.2 minus 0.356 and 7.2 plus 0.356. When I calculate that first one, 7.2, I get 6.844. 7.2 plus 0.356, I get 7.556. And again, we can say it like this: we are 90% confident this time that the true mean hours spent sleeping, lies in the interval between 6.844 and 7.556. Furthermore, if we did this a number of times over a long period of time, 90% of all intervals will fall between those values. So that's how you calculate a confidence interval when sigma is known. The other thing we can do is we calculate what we call a sample size. And so certain times we want a specified sample size, a specified margin of error. If you want to specify a margin of error, you need a certain sample size to do that. If you rearrange the margin of error formula to calculate for N instead of E, remember E is equal to this right here. E is equal to E is equal to Z star times sigma over square root of N. If you rearrange that for the variable N, you get this right here. N is equal to Z star times sigma over E squared. This is called the sample size calculator. And it can calculate the sample size for a specified margin of error. It calculates the sample size for a specified margin of error. And all you need to do to get it, we rearrange this formula, I did it for you. This is what we can use. We need to know Z star, we need to know sigma, and we need to know E. So assume that sigma equals 33. This means that sigma is known, so that means I'm going to use a Z star. Anytime I see this right here, assume this, and I give you the Greek letter sigma, this means that sigma is known. The next class, I'll show you what it means when sigma is not known. You'll have a S instead of a sigma. Question asks, how large of a sample is needed to make us 95% confident that the margin of error is within plus or minus 4? So what is my Z star for 95% confidence? Anybody remind me that? What is a Z star? .96.
1.96.
Thank y'all. What is the margin of error they're telling me to go with right here? They want it to be plus or minus 4. We just need the positive version, so we'll say that's 4. And then the standard deviation sigma is equal to 33. If I want to find the sample size N is equal to Z star, which is 1.96 times sigma, which is 33, divided by E, which is 4. I'm going to take all of that, I'm going to square it. This is a very simple formula to use. You just need to know what Z star is, what the margin of error is, and what sigma is. Z star times the 6 times standard deviation divided by E. When I calculate that, that is 1.96 times 33 divided by 4 is this. I need to square that number. So I square it. I have a squared button here. I get this number right here. Make sure you have like a regular calculator, by the way. You don't have to use Excel for everything. This is easy to use a regular calculator with. So I get this equal to 261.5 people. What's wrong with that 261.5 people though?
You can't have half a person.
You can't have half a person, so what should we do? Round this
Round up.
to, yep, always go up. Always go up. You always go up regardless of what the number is. It could be 261.1. You go up to 262 because you want to be within. You want to be within. In order to be within, you have to be larger. But you always go up on these, all right? That is it for tonight. Do you have any questions?
No, sir.
All right, y'all have any questions? Have a good night. I'll see y'all next week.
Thank you.
Thank you.
Thank you.